Okay, let's look at week 12 examples. So our first one, a simple random sample of 50 items from a population with sigma equals 6 resulted in a sample mean of 32. Provide a 90% confidence interval for the population mean, a 95% confidence interval, and a 99% confidence interval. So the equation we're going to use to find the confidence interval is this, where we have x bar, the mean, plus or minus z alpha over 2 times sigma over the square root of n. So z alpha over 2, we get that from this table down here. And for 90%, we're going to use 1.645. For 95%, we're going to use 1.96. And for 99%, we're going to use 2.576. So we have everything we need in here. We have the x bar, which is the mean of 32. We have the z alpha over 2, which is given one of the three. So we have three different ones. We're going to do all three. Sigma was 6, and n was equal to 50. So we just plug all that into the equation, and then we can just use our calculator, and we get 32 plus or minus the 1.4. And if we do that, we just get 30.6 to 33.4. So our interval is from 30.6 all the way to 33.4. Now, for B, we just change the z alpha over 2 to 1.96 because we're doing the 95%. And then we get to 1.66. So when you do that, it goes 30.34 to 33.66. And when we get to 99%, we use the 2.576. That gives us the 29.81 to 34.19. And as you can see, as we have higher confidence, we get a wider interval. And that's just meaning to be able to get that population parameter to fall within that range and be 99% confidence it's going to fall in that range, that means we're going to have a wider range with the higher confidence levels. Now here it says Nielsen Media Research conducted a study of household television viewing times during the 8 p.m. to 11 p.m. time period. The data contained in the file named Nielsen, which we'll look at in a little bit, are consistent with the findings reported. Based on past studies, the population standard deviation is assumed with known sigma equal 3.5 hours, and we need to develop a 95% confidence interval estimate of the mean television viewing time per week during that 8 p.m. to 11 p.m. slot. So let's go over to our spreadsheet here. So this is our data, and we have quite a few data points. And so to do this, I'm just going to use the data analysis and descriptive statistics. And so we basically have to include that whole column of data. And we'll put the output there, have summary. Okay, so that should work. So we have a mean of 8.5. We have a standard deviation, but we don't worry about that because we have the population standard deviation already known. So really all we need is the mean of 8.5. So if we go back to our PowerPoint, that gives us the x bar as 8.5. We're doing the 95%. So if we remember from the previous slide, that's the 1.96. 3.5 was given for sigma, and n was 300. If we remembered to look at that before we came over, it was from position 1 to 301, so there was the heading, so it was 300 data points, and we solve that, and we get the interval is 8.1 to 8.9. All right, now here's sample. Now I have my heading up here is so I can't see. Maybe that'll help for a little bit. A sample containing years to maturity and yield for 40 corporate bonds are contained in the data file named corporate bonds. Now, what is the sample mean years to maturity for corporate bonds, and what is the sample standard deviation? Develop a 95% confidence interval for the population mean to years maturity. What is the sample mean yield on corporate bonds, and what is the sample standard deviation? And develop a 95% confidence interval for the population mean yield on corporate bonds. So what we need to do again is we need to go look at the spreadsheet. And now we're doing corporate bonds, and we're going to do the same thing. We're going to do a data analysis and descriptive statistics. And here we're just going to go with these two columns of data and output F. That looks good. That'll work. So what we need really is for the years to maturity, we need the mean, and we need the standard deviation. So 9.70625 and the 7.9805. And our yield is going to be the 3.885 and standard deviation 1.619. So with those values, I've already plugged that into the PowerPoint, of course. So that gives us these values here, the 9.7063 and then 7.9805, and also the 3.8854% and standard deviation of 1.6194. And now all we have to do is plug it into this equation, but now we don't know the sigma is unknown, so that's why we're using this standard deviation. And so that's the S, the sample standard deviation instead of the population. So now we're going to look for t values. And t values we have to find in the t tables here. And it's going to look like this. It's the table 2 t distribution. And we're looking at this area. And so what we have to do is we have to look at the degrees of freedom. That's going to be on the left column. Then we have to decide which column to look at. So what t value is, 0.05, or is it going to be the 0.025, 0.01, 0.005? So we have all those choices. And so what we have to do is we're looking at the t of 0.025 because we're doing the 95%. So divide that by 2. And so now we have degrees of freedom of 39, 0.025. So 39.025, so it's 2.023. So you just have to find the right row, right column, and that's what we get there. Now, we know the mean from our calculation. We know the 2.023 from the table. Our standard deviation, we know the 40, that's the number of data points we have. And so we do all that calculation in our calculator, or we could even do it in Excel. And once we do that, we do the plus and minus, and we get 7.1536 to 12.2590 for the confidence interval for the population mean years to maturity. Okay. Now we do the same thing, except now with the sample mean yield, and so we found those already in the spreadsheet. Those are mean and standard deviation. We already know the degrees of freedom is 39, so we have the t is still 2.023. And remember, degrees of freedom is n minus 1, so n was 40. Degrees of freedom is subtract 1 from that, so that's the 39. That's why we're using 39 here. Forgot to mention that above. So we plug all that in and we get the 95% confidence interval for the population mean yield is 3.3674 to the 4.4034. And again, that's just that's the region where 95% confident that that population parameter is going to fall within. Now, if we wanted a 99%, that's going to be a wider interval, and that's because to be 99% confident, it has to be a wider interval. All right, so we're going to use these tables here again on the next problem. Is your favorite TV program often interrupted by advertising? CNBC presented statistics on the average number of programming minutes in a half-hour sitcom, and the following data are representative of their findings. So that gave us all this, and it's in an Excel file. So let's go again and look at our Excel file, and so that's going to be the program. And again, we're going to do the data analysis because we're really interested in just a couple of items, and it's just easier to find them quickly using data analysis. And so we get the mean is 22, standard deviation is 1.119. That's the main things we really need. Now we could have just done that using equals average and then put the data set in, and we could have done equals STD EV for standard deviation and found it that way, but data analysis runs a lot quicker. So back here, so we got our X bar is 22, and that was 1.119, so they rounded it to 1.12, which is fine. So now we just plug all that in. Now we need to had 20 data points. So we have degrees of freedom of 19 and minus 1. So if we go up here, and so it's going to be this column here, so 2.093. And that's what we get here for our t of 0.025. We use our 22 for the mean, that the 1.12 for our standard deviation, and then 20, and we end up with a value from 21.48 for the lower end up to 22.52 minutes for the upper end. So that's going to be our confidence interval. Okay. All right, so the next one, the U.S. Energy Information Administration reported that the average price for a gallon of regular gasoline is $3.94. The U.S. EIA updates its estimates of average gas prices on a weekly basis. Assume the standard deviation is 0.25 for the price of gallon of regular gasoline and recommended the appropriate sample size. Assume the standard deviation is that and recommend the appropriate sample size for the USEIA to use if they wish to report each of the following margins of error at 95% confidence. So margin of error of 0.1, 0.07, and 0.05. So what we're going to do is we're going to use this nice little equation here. So n is equal to the z 0.025 squared, sigma squared over e squared. That's the margin of error. So the z 0.025, that's just going to be our value, kind of like the one we've been using for 95% is the 1.96, and we square that. 0.25, that was the standard deviation they gave us, square that, and then we just put the margin of error down here. Now the key here is we always want to make sure these are all in the same units as far as the sigma and the e. Sometimes you'll get a problem and they'll give you in different units. One will be in just numbers, another one will be in thousands. And so this one might be 25,000 and this one might be 2, but it really should be 2,000. So always check and make sure those are in the same units. So if we just plug that in our calculator, we get 24.01. So that rounds up to 25. You always want to use the next higher number, and you always want to use the whole number. Now, one thing to note is when you have a number less than 30, if you don't have a normal set of data, if something appears questionable, they might actually round this up to 30, so it has that required number of 30 for normality. Now we do the same thing with the 0.07. Plug it in, we get 49. So 49 is a good number to guarantees that there's a margin of error no greater than 0.07. Although to be nice and even, sometimes they might increase it to 50 for this US EIA. They might increase it to the 50 just because it's a whole number, it's round, it's even. Plugging in the 0.05, we get 97. Here, they would actually probably round it to 100 to make it a nice even number rather than the 97. Okay. All right, so the next question. There's been a trend toward less driving in the last few years, especially by young people. From 2001 to 2009, the annual vehicle miles traveled by people from 16 to 34 years of age decreased from 10,300 to 7,900 miles per person. Assume the standard deviation was 2,000 miles in 2019. Suppose you would like to conduct a survey to develop a 95% confidence interval estimate of the annual vehicle miles per person for people 16 to 34 of age at the current time. A margin of error of 100 miles is desired. How large of a sample should be used for the current survey? All right, so what do we know? Well, we know the standard deviation is 2,000. We know the margin of error is 100, and we know we want a 95% confidence interval. So basically, that tells us everything. This is going to tell us we have a 1.96 we're going to use for the z of 0.025. We know the sigma was 2,000, and we know e is going to be 100. We plug all that in, and we get 1,536.64. We'll just round that up to 1,537 to guarantee the margin of error will not exceed 100. Now, if you had rounded down, then you couldn't say it would not exceed 100 because it could, because you're within that 0.64 under, and so it could actually exceed it. That's why we round up. All right, so the next one. According to Thomson Financial, through January 25th, 2006, the majority of companies reported profits had beaten estimates. A sample of 162 companies showed 104 beat estimates, 29 matched estimates, and 29 fell short. All right, so what is the point estimate of the proportion that fell short? Well, 29 divided by the total, which is 162, and so that's just this, and we can divide that out, and we get 0.1790. Now, the p-bar, that's just our sample proportion, so that's what the sample proportion is for part A. Now, part B, determine the margin of error and provide a 95% confidence interval for the proportion that beats estimates. Well, beats estimates is going to have a proportion of 104 divided by 162, and we see that down here, and if we calculate that out, that's 0.6420. Now, the margin of error they want us to calculate, we need to use z alpha over 2 times the square root of the sample proportion times 1 minus the sample proportion divided by n. And so if we plug all that in, 95% confidence interval, we're going to have that's going to be equal to the 1.96 as usual. And then we plug in the 0.642, and then that 1 minus 0.642 is 0.358 divided by the total of 162. Multiply all that together, we get 0.0738. So our sample proportion minus and plus that gives us 0.5682 to 0.7158. That's going to be our 95% confidence interval. Now, part C, how large a sample is needed if the desired margin of error is 0.05? Well, margin of error 0.05, so that's going to be our E, so that's going to be in the denominator squared. And now we just have to use this equation now because we have the proportion instead of the previous one, which was this, which was using the just the means and stuff. So with proportion, we have to do the 0.642 times the 0.358 times that 1.96 squared all over that 0.05 squared. So that gives us 353.18, but we round up to 354. All right. Now, final question, I believe. A poll for the presidential campaign sampled 491 potential voters in June. A primary purpose of the poll was to obtain an estimate of the proportion of potential voters who favored each candidate. Assume a planning value of p star equals 0.5 and a 95% confidence interval. Now, if you're not sure of what the p value is you're going to use in the p star, 0.5 is a safe one. So if you have really no clue about it, 0.5 is what you would use. Otherwise, if you know what the sample proportion is, you can use that as what we did here. And there's a whole list of things, different ones you can use, but usually the key one are the sample proportion or just using that 0.5. So for p star equal 0.5, what was the planned margin of error for the June poll? Well, we just have to plug in everything we know. 95% confidence, that's going to give us the 1.96 here, times the p, which is 0.5, times 1 minus p, which is again 0.5, over n, which they gave us was the 491 people polled. And we multiply all that out, we get 0.0442. All right, so that is the planned margin of error for the June poll. Now, closer to the November election, better precision and smaller margins of error are desired. Assume the following margins of error requested for surveys to be conducted during the presidential campaign. Compute the recommended sample size for each survey. So now we want a margin of error of 0.04 for September, 0.03 for October, 0.02 for early November, and 0.01 for pre-election day. So again, we're going to use that 0.05 for the p star, and all we're going to do is change the denominator. So we're going to put the 0.04 in, can do that calculation, we get 600.25, so round that up to 601. October, well, we go ahead and move that 0.03 here, simplifies basically 1068 after you round up. This one gives us a nice number, 2401, and then when you put a 0.01 in, it gives us 9,604. So you can tell really that margin of error tells us how many people we really need to sample. So if we're really not too worried about it, we can sample 601 and get within 0.04. Excuse me. But if we want to be really good margin of, or really low margin of error, then we have to sample a huge number, 9,604. Now, most surveys that you'll see online or anywhere, they usually use the 0.03. And that gives them around 1,068. Sometimes it's 1,000, sometimes 1,004. It varies, but that's usually the one that you'll see most of the time is that 0.03 margin of error. And that's all I have, so hopefully that will help you this week.